Hello guys, how are you doing today? Today lecture is about how to transform a system with several forces and moments into equivalent system with maybe only one force and one force and one moment. So let's get to it. Okay, lecture 10 for today. Equivalent system of force and coupled systems and distributed loading. Basically, this is what it is about. You have a system with different forces and moments applied to it, and how to convert that in a single unit force and a single unit moment, a single force and a single moment, or maybe even a single force applied at a specific point. This is the typical example. It says if you have a situation like this, imagine this is your hand like it is there holding a bar, and you have two forces applied. The resultant force in the hand is going to be the summation of these two forces acting upward, and that's why the hand is not coming down. But at the same time, these two forces, every one of them is producing a moment, and the moment produced by the force 1 is going to be F1 D1, and the moment produced by the force 2 is going to be equal to F2 D2. So that means that the hand is suffering or is feeling a turning effect also equivalent as the moment of the force 1 and the moment of the force 2. And this system externally, not internally, because internally is different. Internally, if you have the force applied there, it's going to be stress concentrations over there at that point, and it's going to suffer different things. But externally, in the hand, is the same thing, or it's equivalent, not the same thing as having these two forces applied here as a resultant force there, plus a moment. The reason for this happen here, let me go to the dog camera and explain that to you. Basically what happened is, if you have a situation like this, let's say that you have this situation with the force applied here, and I want to determine or convert this force into something at the point A, an equivalent system at the point A. What's happening is that in order for that to happen, I have to take that force F that is there, and I have to move it to the hand right here. This is the force F. I have to move it to this point A. But if I do that, I'm doubling the forces, which is not true, because I'm saying this force is not supposed to be here, this force is supposed to be here. So if I'm moving the force here, this force it doesn't exist in real life, that force over there. So I'm going to put another force here, which is basically going to be the same value for F. And as you can see, these two forces, if this is the point A, these two forces are acting over there, and each one of them cancel each other. So basically, if I do that, it's the same system as this one, externally, once again. Now, what happens if I don't eliminate those forces, and I take a look at those two forces over there? Then I can get the same system that I had on the top, and this force, I'm going to keep it there as is. But these two forces, basically, if I do summation of forces in Y, these and these cancel out. But at the same time, these two forces separated by this distance D, and they create is a moment. Meaning this system and this system externally are equivalent, these two systems. This is the philosophy of how do you transform in one system with several forces, and you convert that force in a particular point, and you can convert it in any other point that you want to. In this case, that is what is happening. Of course, you have two forces. Those two forces I can transport in the same way the two forces here, and then I can convert this system in one force, one resultant force at that point, plus the moment generated by the other forces. And this is what we're going to be trying to do today. This case, for example, you don't have the same situation, because in this case that force is acting through the point, And the only thing that I can do is slide that force here, but this system and this system are equivalent because of transmissibility principle. Remember that there's no moment, there's no distance involved. However, this force is the same one that I explained to you before. If you move this force to this point, you're going to have a force at that point and a moment also generated by the couple that is you are creating there. What for do you do that? Well, imagine that you have that system over there. This is a moment here, this is a force, this is another force, and I want you to imagine how this thing will move in. Of course it's not going to move because it's fixed at the base, but just imagine that I tell you how this tries to move, in what direction it tries to move. Oh, I don't know, this force is pulling it there, but at the same time this is pulling in this way, and at the same time it's trying to rotate in the other way. However, if I convert that to an equivalent system at the base, and I get that at the base, now it's a little bit easier to say how would be the behavior of this element if I just converted in one force and one moment. Now I can say, oh, this reaction here is going to counter this force that is trying to pull it in this direction, and at the same time these bolts are going to produce a moment that are going to counter that effect of the moment that is generated there. So basically what you do for converting that is for simplification and easier to visualize what is happening there. Once again, this is the same example. You can convert this system into that system, and it's easier to see what is happening. And once again, I'm going to reiterate into this. The external effect is the same, but the internal effect is not the same, because this body is suffering different things at the points where the force are applied, whereas this one is not happening. That is not happening. But externally, the behavior as a rigid body is the same. And this is the same, only translation force, and we do that. This is transmissibility principle, or it's also called sliding vector, but it's the same thing. And we already explained that before. And this is the moment. Okay, good. Let's do this example. So we have this example, and in this example, what the problem is asking us to do is find the equivalent resultant force and couple system acting at A, and then the equivalent single force location for the beam AB. Okay, if you read it like that, it's a little bit weird, but basically you should convert this in two parts. The first part is finding the equivalent resultant force and couple moment acting at A. That's the first part. And then the second part says, okay, forget about what you did, and instead of finding a force and a moment at A, find only one force, that's it, anywhere in this line that produces the same effect as everything else combined. I'm going to go in detail and I'm going to explain you each one of them. But the way you're going to do that, every time that you find this statement here, find the equivalent resultant force and couple moment at the point, what the problem really is asking you is find the resultant force, which it doesn't change at all, and then find the resultant moment at that point. And that would be the equivalent system. So let's do that part. Find every component in X and Y, sum or add every component in X, every component in Y, find the resultant force, and the second part this third point corresponds to the second part of the problem, which I will explain later then. So this is the problem that we have. First thing first, we have to find summation of forces in one direction. So let's imagine all the forces that act in X, and the first one that we have in X is the horizontal component of this force here. Well, if this angle is 30, this is 60, right? But if this is 30, the horizontal component is going to be this one here on the top, which is the opposite. So it's going to be 35 sine 30 positive, and this is 25 to the right also. So it's going to be 35 sine 30 plus 25. This is the resultant force in the X direction. And now in the Y direction, we have the vertical component of this one, which is going to be acting negative. If we say positive acts up, this is going to be negative, and it's going to be cosine 30 because it's adjacent. So it's going to be 35 cosine 30 negative, and 20 also here. So it's going to be basically 35 cosine 30 and 20, and both of them are going to be negative or acting downward. Once you have those, you have basically the resultant force. There, if you want the magnitude of the resultant force, it's going to be the square root of this square plus this square, and that's the magnitude of the resultant force. What is the other thing that we are missing? The direction of that resultant force. What is the direction of that resultant force? Well, I know you have to do the inverse tangent of the angle, but I like to know exactly what is the angle that I'm calculating. So basically what I do is with that angle, if I'm calculating this angle here, I'm going to do inverse tangent of y divided by x, but keep in mind that the angle that we are calculating is this one here, this angle. And if you do that, I included the signs, but you don't have to include any sign here. As a matter of fact, I didn't include the sign because I'm doing trigonometry in this part. So if you say inverse tangent of y divided by x, you're getting that angle in particular, and that angle will be 49.8 degrees. Remember, if you have to express it from the positive x direction, then you have to subtract 360 minus that one. Or say this angle is a negative angle. That could be also a possibility. It's not very elegant, but it would be a possibility. Okay, now we have the resultant force and the acting point. Next step is finding the moment, because remember, every time that the problem asks you or demands you to calculate the result, convert the system in an equivalent force and moment system, is resultant force, which we already determined, and the second step is calculating the resultant moment at that point. So resultant moment at that point is just calculating the effect of each one of them. So let's do summation of moments, and assuming that this is going to be the positive direction. In this case, I assume counterclockwise, clockwise positive, but it doesn't matter, you can assume anything that you want to. So if we're going to do that, this force, first of all, this component is passing through the point. Because that component passes through the point, I can slide it there. If the force is horizontal, the distance, the vertical distance between this force and the point A is 0. So that force basically is like not producing any effect. Now this other force here is vertical force, the distance has to be horizontal from here to here. 35 cosine of 30 is the force, and the distance is 2. Now what is the effect? Well, if you look at that point and you put your finger in the point A and you press whatever the force is, the rotation is going to come in this direction, the rotation is going to come in this direction, and that direction, according to my convention, is also positive. So that will be the moment generated by this force. Once again, this force passes through the point, so it's not producing anything. Now the other force is this 20, and the distance, force is vertical, the distance has to be horizontal from here to here. 2 plus 4, 6. What is the direction? If I put my finger over there and I put a pin and I apply this, it's going to rotate also in the same positive direction that I assumed before. And last but not least, then you have this one here, which is horizontal force, vertical distance. The distance should be, if the force is horizontal, the vertical distance between this force and the point is this one, which is 3. So the force is 25 times 3. Once again, put your finger over there. Put your finger over there. Let me use this thing. This is like that. Okay? Kind of like that. Oh, I have the, yeah. So if I apply the force in this end, the rotation is going to be this. So it's going to go in this way. And that way is contrary of my positive convention. That means that it's going to be 25 times 3, and the convention is going to be negative. And that would be my resultant moment at that point. First part of the problem done. Convert the system in an equivalent force and moment resultant system is exactly what we did. Resultant force and resultant moment. That is all. That is all. Nothing new. You learned this before. So we are not including any new thing regarding this problem. Now the second part, which is not new also, it's just an application of what we learned before. So the second part says convert the equivalent system, that system, in only one force applied somewhere in this line. And that has to produce the same effect as before. What was the same effect as before? The force and the moment. The resultant force is not going to change because summation of forces has to be 0, so I can't change. If this force is acting in this way, this force is going to act in the opposite way, and always is going to be like that. The force never ever is going to change. The resultant force has to be the same resultant force. The only thing that is going to change is that before I assume that force was at the point A. Now the problem is telling me, forget about that. That force is going to be somewhere along this line. So I'm going to put that force somewhere along that line, separated by a distance d. And my whole objective is, where should be that d for this force to produce the same moment that I produced before. And the moment that I produced before was that moment we calculated before. So this force located at that distance d should produce that moment. The horizontal component passes through the point. Once again, that horizontal component doesn't do anything, but the vertical component, which we calculated before, it will produce that. So basically my moment doesn't produce anything. So basically my moment, that moment, has to be equal to the force multiplied times that distance d, and from there I solve for d, and that will be the result of the second part of the problem. You should be begging for me to ask you a problem like this in the final. Now, this problem can be twisted a little bit, but it's not any twist. What do I mean by twisting the problem? What I mean by twisting the problem is this. Let me go back to this slide here, the original problem. There you go, the original problem. So let's say that you are here in the original problem, and the problem asks about the point A. What if the problem asks about the point B, and you have a thickness here? Let's say this thickness is 10 centimeters or 0.2 feet, whatever distance. Well, when we were calculating the moment, the summation of forces, no problem. Summation of forces is the same because forces haven't changed at all. But when you do summation of moments at this point, this force, if it's with respect to the point A, is not producing anything. But what if I have a force now, and that force is, I don't know, with respect to a point there, B, right there. What if I have that force with respect to the point B? And I have to calculate the force with the moment with respect to the point B, that point. Well, this force will produce moment equal to 35 cosine 30 times 2, but this other force now will produce moment with respect to this point because we have an actual distance, whatever this distance is. So I will have 35 sine 30 multiplied by this distance, and that will produce a moment also going in this direction, which is positive. And this force is only one component because it's this one, but this force, now the distance will change because instead of being 3, that will be 3, but the minus this other distance. So the actual distance will be from this point to this point, which is where the point B is. And sometimes I have asked that in the exams, and a lot of people mess up with that question just because they forget about that distance, even though I explain it and explain it and explain it. Okay, let's try the same problem now, or the same type of problem in 3D. And you have this situation. And this is a problem from the book also. It says the building slab have 4 columns and F1 and F2 are 0. F1 and F2 are 0, meaning they shouldn't be here. Real life, I don't know, maybe they are decoration, maybe they are redundancy, I don't know why. The real reason here is because the problem reuses, the book reuses this problem for another scene later on, and they say F1 and F2 has these values. But for our purposes, this doesn't exist. So I only have these 2 forces here, and the problem asks me to find an equivalent system at O, and then find a unique force somewhere in the plate to produce the same effect. And this is a very important problem in foundation engineering, because the center of the forces, the vertical forces, is going to be also the center of pressure in that soil. So how do we do this in this case? In the same case that we did before. The only difference is now we work in vectors. So first thing first. What is the first step? Calculate the resultant force. Quick, what is the resultant force there? 5, 4, 3, 2, 1. Is there? What is the resultant force? 20, 50, 0, 0. Resultant force, 70 K. Direction negative, going downwards. That's it. First part done. Second part, moment with respect to the origin, that point over there. How do I calculate the moment? I need the arms for that moment. So basically I'm gonna have R cross F, and I'm gonna do the summation of R cross F everywhere. Why R cross F? Because we're working with 3D. You can do it differently, but I don't want you to do it differently right now. So R cross F, what is for this force? What is R? R is from here to, I know it looks slanted, I haven't told that before, but imagine you have an ample imagination. Imagine this follows the axis, and don't make me switch it and change it. So the arm is from this point to that point, and that's 10. In what direction? In the positive I direction. So it's gonna be 10I cross multiply by negative 20K. That's the first one. And the second one will be this and that. This is I and this is J. So how much in I? 4I. How much in J? 3J. So basically the arm is 4I, 3J, cross multiply by negative 50K. And then you multiply and you say, okay, I cross K, remember the little circle that I explained you, right? IJK will be positive, IK will be negative J. Negative J times negative is positive J, so it's going to be 200J. And then here you have I cross K, same situation, is negative, with this negative is positive, 200J, and J cross K is going to be positive I, but I have the negative sign here, 3 times 50, 150. Add these two now, negative 150I plus 400J. I want the magnitude of that resultant moment, square root of this square plus this square. That's it, that's basically it. But that's the force. I want the direction of that moment, alpha, beta, gamma. Get the magnitude, get this divided by the magnitude, that's going to be cosine alpha. This divided by the magnitude is going to be cosine beta, basically. Now, second part of the problem tells you, forget about what you did, figuratively speaking, because you don't forget about what you did. You're going to use it here. Forget about what you did, and now what you're going to do is basically place only one force somewhere in that plate. I don't know where, so I'm going to call that distances xi and yj, and that's my objective. That resultant force, which I know multiplied by that arm, has to be equal to that moment. So basically xi, yj cross multiplied by my resultant force, which is negative k, has to be equal to that. And then when I do that and I say I cross k is going to be j negative, but then with the negative is going to be positive, so 70xj, and this 70y and j cross k is supposed to be I, but I have this negative here, so it's going to be negative 70y I has to be equal to this, and then everything that goes in I has to be equal, and everything that goes in j has to be equal. So basically that's what you do. 70x has to be equal to 400, and negative 70y has to be equal to 150, and then you get the location of the unique force, which is the resultant force. And this is another problem that I asked this in a bunch of homeworks, by the way. And I have asked this problem also in the exam, and a lot of people fail. I don't know why, because it's extremely easy to do. So that's it for moment resultant of a moment, converting a system of forces and moments in equivalent system. So a general system of forces and coupled moments acting on a rigid body can be reduced to single force, single moment, single force and two moments, single force and single moment. What do you think? Actually, we did this, right? We just demonstrated that it could be a single force, but we also demonstrated that it could be a single force and a single moment. And why not? It could be also a single force and two moments if I want to. What I don't think is possible is this one, single moment, only if the summation of the forces is 0 and there's no resultant force, maybe. But I think the problem, the quiz was intended, or this question was intended what is the minimum amount of actions that you can convert the system to a single force at a particular point. I think so. But it could be also a force and a moment, because we did that. The original force and couple system and the equivalent force couple have the same internal, external, microscopic, internal, external effect. Well, I explained this before, and I say the effect is external only the same external effect. The other part that we have to talk today is about distributed loading, and I have like no more than 15 minutes because I have to run to class now. But distributed loading. And when I explain this in the classroom, basically I go and even I pull a chair and I put it on top of the desk to show what is happening, and I'm not going to do that here. But I say, imagine just this pen here, and I'm going to get this pen and I'm going to put it on top of this cell phone. I hope it doesn't break it. I don't break it here. So if I put this thing here, if you have to represent this force here, this force on top of the cell phone like that, you put an arrow, because that's what you do. And that's okay, and that's a concentrated load. However, if you look at the tip of this pen, the tip of that pen is not the point. There is a surface here. So that means that whatever force I am applying from the top is getting distributed along this area. What happened in the majority of the cases like this is that you assume that, oh, that area is small, so I'm going to consider that the whole force is applied at that point. But that's not the case. Usually it's not the case. You can do that, yes, but usually it's not the case. If you have this bunch of wood here, lumber, that lumber is, I mean, I know the total weight of this is going to be acting somewhere at the center of that part, but in reality it's distributed, because it's not that only the center weights, it weights here and here and here and here and here and here, everywhere. But if I want to ask the total effect of this block, where it's going to be acting at the center, and that's something that you know for empirical reasons, you know, because you have done it before. And yes, I know that is related to the center of gravity, but we haven't covered that material yet. But in reality, it's going to be acting at the center of gravity, or could be considered to be acting at the center of gravity. And those are equivalent system also, or distributed load converted in single concentrated load. What is the reason for doing that? Well, again, externally, from the point of view of reactions, the effect is the same. Internally, or whenever you do shear and moment diagrams, which is going to be it's going to be chapter 7, you do not do that. You do that only for calculating reactions, and that's it. Calculating external reactions. But when you calculate internal forces, forget about doing that, because then it doesn't have any correlation. Look at that beam, for example. That beam over there has these sacks over there, and you can simplify or not simplify, assume or represent those weights at different rectangular distributed loadings on top of that. Why rectangular? Because the idea is that the weight per linear, the weight per length doesn't change. So if I go the first meter on this beam, I'm going to have 1.5 kilonewton. And if I go the second meter, only the second meter, I'm going to have also 1.5 kilonewton, and so does the third meter. Now, if I go here the first meter of this load, I'm going to have only 1 kilonewton. If I go here the first meter, I'm going to have 2.5 kilonewton meter. If I want to represent just the load coming from here, how much will be the total load coming from here? Yes, the first meter 1.5, the second meter 1.5, the third meter 1.5. So the total load coming from here will be 4.5 kilonewton, and that will be applied at the center. That makes sense. That's something logic. That's something that you have done before by inspection. What is the total load here? 3 times 1. What is the total load here? The first 1 meter is 2.5, and the second half meter then has to be half of that. In other words, whenever you have to represent or convert a distributed load in a concentrated load, what you do is no other thing than calculating the area of the shape of that distributed load, and that will be the total load. And the resultant force will be applied at the centroid of that shape, which for a rectangular area or a square area is at the center. That's the only thing that you have to remember for this part. If you have a parabolic section like that, it doesn't matter, it's going to be at the center. Oh, what is the center? We will discuss that later. But for the time being, right now, it's at the centroid or the center of gravity of that section, and the total force is going to be the area. And we're going to be working, this is the way you calculate the centroid. Don't mess up with that right now, but in a couple of lectures I will explain that. Centroid is in the tables that you can find in the back of almost every book. The location of the centroid is there, and also is the area of the section, so you can get used to that. For the purposes of the first exam, which is the one that involves this part, we're going to be working maybe with rectangular load, distributed loadings, and triangular distributed loading. So what is the location for a rectangular? At the center. What is the area of a rectangle? Height, which is the value of the load, times the base. So the total load is going to be 4,400 times 10, located at half of the length, 5 feet. What is the area of the triangular load? Base 600, 6 times height, 600 divided by 2. 6 times 600, 3,600 divided by 2, 1,800 Newton. Now the location is at the center of the triangular shape, and the location is 2/3 from the acute angle, or 1/3 of the base from the right angle. 2/3 of 6 is 4, 1/3 of 6 is 2 from this end. And that's the only thing that you have to know. Examples of rectangular loads, basically self-weight of the elements. If the elements are constant in area and constant in density, like the roof, for example, usually is rectangular. Triangular load, and typical example of a triangular load is the pressure of the water or the pressure of the earth, because every time that you go under the water, remember that triangular, let me go back here again. Remember, whenever you are, if this is a fish tank, a pool or something, and this is the level of the water, and this is h, the total height of the water. So basically the pressure over the walls here, this pressure is going to be like that. The force is going to be this triangular distributed. If you call this distance y, as you're coming down from 0 to h basically, and the unit weight of the liquid is gamma, the pressure here is going to be the total gamma h, this distance here. So that means that the total force is going to be acting somewhere on the walls like that. The total force, no, the representation of the total force is going to be acting somewhere here, and it's going to be h times gamma h divided by 2, and the location from here to here is going to be 1/3 of h. Another typical example of triangular loads are you can consider earthquakes or even wind. Wind is more parabolic like that, but there is a part of the wind that starts like this and then do that, and it can be considered kind of, for simplification, triangular in that part. But hydrostatic loads, basically, hydrostatic loads. So what is our objective after doing this? If you encounter any distributed load like this one, our objective is just convert that in concentrated load and continue. So imagine that you have that problem and you say, given the loading, find the equivalent force and its location from point A. Equivalent force and its location from point A. That means, once again, find the resultant force and moment at A, and then find the location of the resultant force only. The problem is that we have to convert this and simplify it to whatever we know. And what we know is concentrated loads. So I don't know what is the trapezoidal, but I'm going to convert it in a triangular and rectangular load. And basically, I'm going to solve it exactly as the previous problem that we did. So first, I can consider this like a rectangular load, because it is, and this height here is 0.5 kilonewton per meter, and the total distance here is 3, meaning the total force, or the total area, is going to be 3 times 0.5, and that's going to be the value of that load. And I forget about that rectangle anymore. Now the location, I know it's going to be somewhere in this line, and that somewhere, because this is a rectangle, is going to be half of the base, 1.5. Now, what about the triangular load here? Well, how much is this height? 2.5? Nope, it's not 2.5. 2.5 is the total, and I already used 0.5, so the distance here, the height, is going to be 2, and that's my triangle, 2, and the resultant force is going to be the area, 2 times 3 divided by 2. That means that that value is going to be 3 kilonewton, and once again, it's going to be somewhere in this line. And what is that somewhere in this line? 1/3 of the base from the right angle, 2/3 of the base from the acute angle. That's basically what we have. 1/3 of the base, or 2/3 of the base. Once you have that, forget about the triangle, forget about the rectangle, put your two loads over there, and proceed. At point A, what is the resultant force? At any point, but at point A, not considering the support, external forces only. Well, it's going to be this value 3 plus this value 1.5. Don't forget this 1.5 that was here. So my resultant force is going to be 1.5 plus 3 plus 1.5, 6 kilonewton. Moment with respect to the point A. Okay, summation of moments, I consider this positive. So it's going to be 3 times, what is the distance? 1.1 meter here. 1.5 times, what is this distance? 1.5. 1.5 times, what is this distance? 3 plus 1, 4. All of them are coming in this direction, which is positive according to my convention. 3 times 1, 1.5 times 1.5, 1 times 5, 1.5 times 4. That's my resultant moment. Oh, but I don't want the resultant force at A and the resultant moment at A. I want just one force acting somewhere there, that produces the same effect. Well, it's the same thing. What do? You place the force somewhere else. Where is that somewhere else? That distance, we call it D. And then we say that that moment has to be equal to the resultant force, which is 6 times D. And we solve for D. Same problem that we did before. Usually at this point, I go to the students and I ask like a class activity. But in this case, what is the resultant force? At the centroid of that shape, period. What is the value? The area of that shape. The line of action passes through the centroid. The resultant force is the area. That's basically it. What is this located at? 1/3 of here, 1/3 of, 2/3 of here. 1/3 of 12 is 4. What is the value of the resultant force here? 100 times 12 divided by 2, 600. X equals 4, because it's 1/3 of base from this angle. I usually do this group assignment, and the only thing you have to do here basically is the same that we did before. You use this triangle, and then you convert this in one rectangle here and one triangle there, and that's basically it. So that's it for today, and I have to go to class now, the real class, I mean. See you later in the next lecture. Try to be good, guys.